Good morning, this is Jim O'Brien. I'm going to do a Mudflow webinar today for Flow2D users, and this will be the first of two webinars on Mudflows. We'll talk about the physical processes of Mudflows today, and then on next week, I'll talk a little bit about sediment availability and sediment yield from a watershed that helps to generate mudflows. So to get started today, this is our kind of annual or semi-annual Mudflow webinar, and Flow2D has the ability to simulate mudflows. And what I want to highlight today is the differentiation of hyperconcentrated sediment flows or mudflows versus clear water or mudflows and mudfloods. So let's get started. In Flow2D is a finite volume conservation model, and what Flow2D does with sediment concentration is to conserve the volume. So I try to take a practical approach to this, where the objective is to match the potential available sediment supply from the watershed with the water volume for a given design flood event, meaning that you have to estimate the sediment volume to make sure that it makes sense, and then compare that with the sediment concentrations that you're imposing on the model or the sediment volume directly in order to see if you can have a mudflow event. And if you can't, then perhaps, and that's specifically true for, say, a 100-year event. If you can't, then you're not going to have a mud flow, you'll have a mud flood is what I call it. And we'll see that in a minute. So we'll talk about the fluid properties of the mud flow and how the model treats this as a continuum, meaning that there is no exchange of sediment with the bed. The flow only ceases to flow, or it can remobilize, but we're not scouring and depositing out of the flow onto the bed. And I'll talk about that a little bit later with respect to a two-phase flow model that we're starting to work on to put into the model. So the idea is to predict areas of inundation and the maximum hydraulics associated with either clear water flows or mud flows for a worst case scenario, and this will allow you to delineate the hazard. So I want to start by identifying a few basic concepts related to hyperconcentrated sediment flows. And the first is concentration by volume, which is pretty basic and simple. It's just the volume of sediment divided by the total volume, or the volume of sediment plus the volume of the water. So this is concentration by volume, and I'll refer to this repeatedly throughout the presentation. The second is internal to the model, but you should be aware that it calculates the specific weight of the sediment mixture. So it takes the specific weight of water and the specific weight of sediment and adds the concentration by volume that you have as an input parameter in order to get the specific weight of water of the combined water and sediment. Okay, and then finally there's the bulking factor. And the bulking factor is just 1 minus the concentration by volume. And this is important because it allows you to understand how much an increase both you have in the volume of a hyperconcentrated sediment flow, plus how it affects the peak. So if you have a concentration of, say, 50% by volume in a given flow event, then 1 minus 50% is 0.5, and 1 over 0.5 is 2. So if you have a concentration by volume of 50%, you're going to have a bulking factor of 2. So in this case, I'm showing you a picture here where you see a flood event in western Colorado, this is. And you can see that this is a highly turbulent, rapid flood event. And it looks like it's, very deep dark brown color. And so I always ask the question, what do you think the concentration by volume of this mixture is? And in this case, you can hear the boulders and so forth bouncing, rolling along the bottom and so forth. And I went down on the other side of this bridge and I stepped out into this flow in a place that was relatively safe and grabbed a mixture of the water and sediment right near the shore, so that you had an estimate of what the fluid matrix was in this case, of the totally mixed sediment, but not the boulders, obviously. And in this case, the concentration by volume was only 22%, but 22% is pretty significant. If you had a flow that was on the order of 25%, you would be increasing the concentration by about 20%, or I mean the total volume and the total and the peak discharge by about 20%. So I mean, when people design bridges and culverts and so forth for clear water flows and don't consider the potential, excuse me, of having sediment, at least 20% concentration by sediment, then you're missing about 20-25% of the actual design flow of the bridge. So most of your bridges are actually under designed in that regard. So this becomes an important table for understanding mud flows and mud floods and water flooding. And let's start at the bottom. If you have a water flood, typically you're going to have a bed material load or a bed load and a suspended load combined. And that's this conventional suspended and bed load actually only has been measured in typical river systems up to like on the order of 10%. And most of the time, the sediment concentration is more like on the order of 2 to 5%. So I'm allowing an extension of this, say up to about 20%, that you might be able to predict with typical sediment transport equations, a concentrate the fluid motion and so forth by limiting it to water and just calculating a conventional suspended load and bed load on the order of 20% concentration by volume. Above that, then the particle interaction with the fluid and the particle-to-particle contact begins to have an influence on the fluid behavior. So the flow behavior. So the fluid properties in this case become important, and I call between 20% concentration by volume up to about 40-45% concentration by volume a mud flood. And in this case, it still basically behaves like water. There may be, if you read some of these, marked settling of gravels and cobbles, flow spreading nearly on a complete horizontal surface, liquid surface with two phases appearing, waves travel on surface. And the flow mixes easily. If you get into a range of about 45% to 55% concentration by volume, then the fluid properties and the concentration by volume influences the yield stress and the viscosity, such that the viscous stresses in the flow become dominant essentially. And you may have what you would consider to be fluid flow. It could be a slow creep sustained mud flow. There might be plastic deformation under its own weight. It's cohesive. It won't spread on a level surface. And down to say 40 to 48% flow spreading on a level surface, cohesive flow, some mixing. Now this extends a little bit both above and beyond this range depending on the type of clay material or the percent of clay compared to the percent of silt or silt clay mixture. So above this amount, 55% concentration by volume, it's essentially a landslide, and now you're walking on it. It will not flow. It's a failure by blocks sliding or by tumbling blocks with internal deformation during the slide. And what I did to generate this table was I took actual set mud flow deposits throughout Colorado and Utah and brought them back to the lab and simply, dried the samples, burned off all the organics, sieved out all the gravels and cobbles, and played with the fluid mixture, added by taking the dry sediment and adding water to it in a known amount, mixing it, putting it into essentially like an aquarium, and jostling it back and forth and making some observations. So this is how this table was developed. And when you have a fairly classic mud flow, one of the things that one of the features associated with these is the occurrence of a frontal wave, where you have a lot of boulders or maybe organic debris, logs, and so forth. In a more urban setting, this frontal wave might be filled with urban debris, balls, junk, refrigerators, and so forth. One of the things to note when you see a mud flow is that there's a very clear shear zone that occurs if you look down upon it. Now, this shear zone will occur throughout the flow event, and it'll make it more U-shaped. The actual flow inside the channel will become more efficient by making this U-shaped, and you'll see the shear zone occurring along the surface here, but it's actually under the flow, and the flow in the interior often becomes mounded a little bit. So these shear zones become important. Now, I want to differentiate this from what you might see in the field in some locations, Savage and others. If you look up Savage with granular flood and flow events, you'll see that these are mostly cobble bouldery events that kind of flow with just a little bit of interstitial fluid, and then they become mobilized, mostly like billiard balls, and continue to flow down slope, requiring very steep slopes to maintain their motion. These are quite rare, but I wanted you to distinguish those. And then I don't want you to be fooled by surface washing, which might occur after a mud debris flow, quote, event. If you go in and actually excavate this, you may see the mud flow material underneath, but the surface material has become washed by repetitive surges of water flow during the falling limb of the hydrograph. So I want to show a couple of movies to further highlight the delineation between mud flows and mud floods. So I'm going to start with a mud flood here, and let me shut off the audio first. Okay. Now, most of you may have seen these in the past, but I'll because they're pretty definitive in terms of a mud flood. So it's raining, obviously, both here and in the watershed, and the flood's going to arise. So I'm going to move this ahead until and you see the water flowing here. And I want you to note the arrival of the flood wave is going to have a bouldery front, maybe some debris, and it's going to go over, here it comes, and it's going to go over this Sabo Dam type of works here and lift these boulders off, and these will become part of the frontal wave. So here comes the frontal wave, and you'll see that it's moving a little slower than once the peak arrives. And that's because of both the interaction with the friction in the frontal wave and the fact that these boulders are kind of holding the flow back a little bit. But this is the typical railroad express that you hear in some side canyons in the western United States. And if you hear these, boy, you better get out quickly, because it's only a matter of minutes or seconds even before they arrive. So I wanted you to see this. Now, this is what I would delineate as a mud flood event. It's probably on the order of 30 to 40% concentration by volume, or say 25 to 35% concentration by volume. Lots of splashing, not much boulders or anything on the surface. It's you know, hardly any organics on the surface now, but it's high concentrated sediment flow, but not necessarily a mud flood. I'm going to move this ahead a little bit so that you can see kind of the slurpy nature of this. And you can see that the roll waves, or not roll waves, but the turbulent surface waves on this are pretty rapidly dissipated. And you do see a shear zone here too occurring. So this is approaching more of a mud flow phase. So let's take another look at what now might be called a mud flow event. Well, not might be called, that what is called a mud flow event. Again, I'll turn this off. And this particular mud flow event, someplace in Switzerland or Italy, obviously they have had these type of events here in the past. Little humorous nature here. People must be accustomed to dealing with this event, but you can see some debris there in the frontal wave. But what's notable about this is watch the natural levees form to confine this flow to a conveyance channel facility. Picks up this car on the other side and moves it. You can see some material. She's obviously not that worried about it at the moment, but she ought to be, I think. And you can see that this created this natural levee phenomenon. Sometimes these natural levees consist of boulders or a bouldery type levee. And this is clearly a viscous, gloppy mud flow event. And now I'll stop this one and show you one more set of these. And hopefully this will run here. I think so. So here is what I like to show at this point. I mean, we'll go back a little bit. Here's what this looked like before this event, and now we're already into the phase. And this mud flow is interesting because it's relatively low flow depth, but it has the ability through buoyancy and weight and specific weight of the flow itself, the fluid matrix, to mobilize some pretty heavy debris. Obviously, the frontal wave came down and deposited a lot of boulders on the other side. They didn't show this, but so you can see this event moving rather slowly, and I'm going to move it ahead a little bit here because I think you get the idea. One thing that has occurred over my 30 or 40 years of dealing with hyper-concentrated sediment flow events, and I attended the first annual Mud and Debris Flow Conference in Davos, Switzerland, is that the number of videos that are available now that show mud flow and mud flood events is significant. And so back in the 80s, 70s, and 80s, there were very few, maybe one or two that actually showed something that, you know, was of this nature. Now I'm going to move ahead and show you something. You can see that the event has altered the immediate environment significantly. Now, looking downstream, just to give you a further taste of this, here's another location there's the house that you saw in the previous security camera view. And once again, this is notable because I think this channel went through over here, and the channel is completely filled with mud and debris, and now most of the flow happens to be going over bank through this logging or log mill or log timber company. And as you move along here, you can see that it's, even though again it's a fairly shallow event, the force by which this has the capability of moving some fairly substantial structures and so forth is significant. And then a little further downstream, and finally move this ahead to where if you had asked me when I started this footage if I thought that the pillars and so forth would collapse under the mud flow, I would have said no. And so this is pretty amazing. Okay, so I think I make my point here. Let me escape this, get this off for you. So these are available to you if you wanted to. I can give you these. If you email me, I can provide you with these 2 mud flows that I have videos of, but this is the link to watch this last one. So let's talk a little bit now about how to model these kind of events. I use not only the full dynamic wave equation, but I solve this shear stress equation, shear stress versus rate of strain equation for the velocity to create a seed velocity to put into the full dynamic wave equation. And in doing so, I have the viscous stresses here, plus the turbulent stresses here, where the coefficient C represents, if you were to look at a typical water flow, this would involve the von Karman's constant and a mixing length and 0.4 for the turbulent flow. And if you had turbulent flow, then these 2 components, the yield stress and the viscosity, being a linear rate of strain here, would be negligible. Likewise, when the viscous stresses, the yield stress and the viscous stress here are significant, the coefficient for turbulence and dispersive contact become negligible. So in this plot of shear stress versus rate of strain or rate of shear, if you wish, if you had pure water or clear water, you would have Newtonian flow in which the shear stress is a linear relationship with the rate of strain, and the coefficient in this case is nothing more than the slope of this line, which is the viscosity of the fluid. So this would be a rather small value for water. Then if you have to overcome a yield stress in order to initiate motion, then the relationship is referred to as a Bingham fluid, and this would be a pure laminar relationship where the shear stress is a function of after it's exceeded the yield stress, a function of the viscosity times the rate of strain again, where the viscosity is significant in this case. So, and then finally, we have both a pseudoplastic model, which is uncommon in fluids, more common in a manufactured type of substance where increasing the rate of shear or strain results in a reduction of the shear stress on the fluid. or if you want to go backwards, increasing the rate of shear stress results in a higher rate of strain or vertical velocity distribution. What's prevalent in the viscous nature of mud and debris flows is that this is a summation term here, where as you get into higher orders of rates of shear, where beta in the previous equation is 2, then this, as you escalate the rate of or the increase to shear stress on the bed, the rate of shear increases, but not as significant as it would be for a linear or Bingham fluid. So I went out and gathered all these different samples and brought them back and created a laboratory viscometer, which I measured the rate of strain and on an annulus and on a fluid in an annulus, and measured the rate of strain as I increased the rate of shear, meaning that I increased the speed of a rotational viscometer, and then measured the rate of strain and the shear stress on the interior measurement module. So I created both for the shear stress and for the yield stress and for the viscosity. I created these relationships as a function of the concentration by volume. So for each one of these relationships, I have to generate this plot in order to come up with an appropriate slope. So I need a number of points along this line. So I have to take a number of measurements in order to get this relationship. So it takes about 10 or so of these measurements along this line to get one viscosity and yield stress for one concentration by volume. And then I need like 10 or 20 concentrations by volume in order to make this exponential plot. Now, I did this back in the early 80s. And as you see here, some other people were doing this at the same time as me, and I didn't know it. And I later got their data. And so they came up with the same nature or rough formula that I did. We did this all independently. And there was one person back in the 30s and another person in the 50s that also did this, and other people since, both from the Cascades Volcanic Observatory in Portland, Washington, and over at the Swiss Federal Institute, have also done measurements and used exponential relationships. So this is a common form of relating the shear stress, the yield stress and the viscosity as a function of the concentration. So if you plot all of these together, you can see that there's a general range, not only for the data that I put together, but the data that others have collected. This is the yield stress, this was the viscosity. So you see how these kind of fall into a general envelope. Now, the way that I would approach this, later I'll discuss this, but I may not come back to this plot, is to understand at your location what the nature of the sample deposits that, or samples that you might collect from a deposit might have in the way of silt and clay percentage in the actual volume of the material you collect in the sample. So if you have a general understanding that you have a lot of silt and clay, or a lot of clay if you do a hydrometer analysis, and the clay is a dominant um, component, say 10 or 12% of the silt and clay volume, then I would look towards having higher yield stresses and viscosities as a function of concentration. If it's fairly fluid and you don't see much in the way of deposits on your alluvial fan or surface that exhibit clear mud and debris flow type of phenomenon like berms and frontal lobate deposits and so forth, and it's fairly fluid, then I would select maybe a sample or back in this range. So I want to discuss this a little later. So again, back to my equation where I have the viscous component and the turbulent dispersive component to my shear stress equation here. This coefficient is a function of turbulence and dispersion. So I want to talk about this for a minute. The dispersive stress, well, first let me mention in a general sense that the fluid shear stresses in high concentrations of sediment flows have several components. One, the cohesive stress, which is really the fine particle interaction due to the clay, and the cohesive behavior of the clay as being a hydrophilic type of fluid matrix. That is, it likes water, and so it will actually the particle alignment and so forth will be such that it bonds the material together in and there's a cohesive stress that goes with this. Then there's the viscous stresses, which is the combined interaction of particles and the surrounding fluid. An inertial impact that comes from an inertial stress that comes from colliding sediment particles, and this is the billiard ball effect. In order to have a billiard ball effect, then you have to have a significant vertical velocity distribution such that the higher layers of the flow are flowing faster than the lower layers, and the particles in the upper layer then are moving faster and can dissipate this momentum, the energy, and transfer the momentum to the boundary in this manner. And in order to do that, you essentially have to have turbulence in the fluid. So you have fluid mixing and sediment particle mixing. So these are the general and most important stresses in the flow event. Now, I did a lot of research for my PhD and for papers that I published afterwards back in the 80s on the nature of viscous stresses versus turbulent dispersive stresses. And I'm not going to bore you too much with this, but in order to have a dispersive stress, you have to have a high concentration of sediment, approaching, say, 40–50% concentration by volume. You have to have a fairly significant velocity gradient in your vertical velocity profile, something on the order of 0.1 inverse seconds. And then you have to have particles that are on the order of at least 1% to, say, 10% of the flow depth. This is what gives you the billiard ball effect. Now, what I want you to glean from this table is that as you increase the concentration by volume, then the resistance to flow increases internally. And so I created what I would call a dispersion or dispersive resistance to flow as, quote, a Manning's kind of turbulent end value here, as it relates to the turbulent end value that you would normally assign in channel flow. So I did this, I made this calculation. We verified some of this analysis with high concentration of flows that went up into 20% and higher, um, from some work done at MIT laboratories back in the 50s and 60s. And some concentrations that you might relate to is at 56% concentration by volume, it's a maximum packing factor for spheres. At 65%, or sorry, at 61.5%, this is Bagnall's maximum sediment concentration. That means it's if you take the maximum packing factor, if you had nice uniform spherical sediment particles and you pack it with other silts, clays, and fine material, fine sands, you could increase this packing factor up to about 60%. And this is Bagnall's laminar concentration coefficient. The lambda is here. And you have to go to Bagnall's papers to understand where that comes from. And then finally, as you approach actual ground conditions, 74% or and higher, you can walk on this. So the porosity is, in this case, is like 36 to 40% in this range. And in order to have motion, if you start out with a landslide, in order to have motion, you've got to decrease the concentration by volume. And then it flows faster and faster, the particles separate, and so your concentration goes down. So I put this turbulent dispersive relationship also into an exponential form and created it or formulated it in such a way that I hardwired this for you. So if you put in a turbulent end value for your channel and so forth, it will create an additional resistance to flow for mud and debris flows that's related to this dispersive stress. So the dispersive stress then can transfer more momentum to the boundary by particle contact. And this is all hardwired in the flow. So you don't have to do anything other than assign a turbulence end value, a turbulent end value that you would have for natural conditions for a flow on the surface condition. So for each study that you're going to do in a watershed or alluvial fan or something, or area that has mud flow characteristics as deposits, you should go into that watershed fan, learn a little bit about the geology and the soils and what unique rheological properties they may hold in discrete conditions for that particular watershed. So there are two possible approaches that you could take to do this. One is to actually go and get a viscometer and perform laboratory viscosity and yield stresses that I did back in my college days, my graduate studies. Or the other choice you have is go to the tables that I showed you and select parameters from the existing data given a specific nature of the plots that I showed you, either high viscosity, moderate yield stress, or high yield stress, moderate viscosity, or low yield stress, low viscosity, so forth. Now, a couple of comments about laboratory analysis. This obviously lends an entire layer of complexity and requires additional budget and time and effort for you to perform this, but then it will make this much more accurate from a unique watershed or fan perspective. However, the cost of doing the laboratory analysis have come down because there are viscometers, Brookfield, Massachusetts, corporation has laboratory viscosity viscometers for things like asphalt. And you can use these to do mud and debris flows. And the cost of these is on the order of about $1,000 to $2,000. I have not done this with one of these viscometers, but I think from what I've read about them, it's entirely plausible to take and generate a fluid matrix, sieve out the cobbles, and you could leave some fine gravels if you'd like, or the sand material, and do these viscometer analysis, as I mentioned to you, doing 10 or so points in order to plot and get the slope of the line as a viscosity and see what the yield stress would compute out to be. Now, it's very important for you to realize when you do these tests that in the field, mud and debris flows have very low rates of strain. You will see some laboratory data that may have hundreds of inverse seconds or even thousands of inverse seconds. That is, they turn these viscometers on and they're spinning them wildly in order to estimate the viscosity. And that's not the case. I mean, what is happening when you do that is you're just getting a shear layer in there and slippage between the fluid. So it has a slip boundary and it's just sliding against itself. And if you look down on the viscometer, that's clearly the case. If you can estimate what the yield stress, the yield, the shear stress, the shear rate should be by just taking a mean flow depth and estimating what the velocity is and plotting it as a linear rate of strain, and then you can get the rate of strain value, and you'll see that it's orders on the order of a tenth of an inverse second, maybe up to a half of a or 1 inverse second. So I caution you if you're going to do that. The other choice is to select from my table or other published data some parameters in order to compute the yield stress. So in summary for the lab work, build, buy, or rent your own viscometer. It's expensive to do this. Or a simplified approach, observe some post-field conditions, identify that it's a mud flow, collect some undisturbed fluid matrix samples, clean, dry, sieve the samples, and then analyze the behavior of these samples by concentration, by volume, by re-wetting the samples, and then select an appropriate comparable condition from the table that I showed you previously. So if you select the viscosity and yield stress parameters from table 9 to match some field conditions, say high viscosity and low yield stress, again going back to this table, Glenwood number 4, I would recommend or can suggest to you has a relatively high viscosity and yield stress for a mud flow event, and it's representative of taking a wet cement, say, in your hands and making a ball out of it and throwing it on the wall, and it sticks. And so this is the nature of this Glenwood 4 sample. Some of the Aspen mine and Aspen pit samples are relatively low viscosity and yield stress. So this is how that I would analyze some samples, see what percent clay you have in the material, and whether this looks like it would be a very viscous, gloppy type of cement-like flow. And then you could use this with some degree of certainty that you're going to have a viscous cement-like flow. So select the viscosity and yield stress parameters to match field conditions. compute the viscosity and yield stress for one concentration by volume, and then see how this looks with the plots that I had of this, whether it falls inside the range or the envelope of values that I had. Try several relationships for one inflow hydrograph and sediment concentration. So, you could try several of these and see how it affects your flood hazard delineation. Compute the viscosity, the sample viscosity and yield stress for one concentration by volume, and then try a sample with a high viscosity, high yield stress, or high viscosity, low yield stress. A low viscosity, high yield stress is probably unlikely. If you have a high yield stress, you're probably going to have a high viscosity. So you could try different samples, put it in your model, different relationships, put it in your model, and see what you get. And try several of these for one inflow hydrograph and one set of sediment concentrations, and see what impact you have on your area of inundation and your maximum velocities. So there is one other parameter that I have in my yield stress versus rate of strain relationship, and that's this, for the viscous stresses, I have a laminar flow resistance parameter. And this occurs for laminar to transitional flows. It was measured by some researchers from CSU. Woolheiser, back in 1975, created some range of laminar flow resistance factors here. But what I did was I plotted these also versus actual N values for typical comparable surface resistance. And so if you assign a K factor in Flow2D, it will automatically compute a K factor for use in this equation from the N value that you've assigned in the model. So let me show you a typical pattern of results. Here's an actual case from Colorado Springs. This is the water type of flood event, clear water type of flood event. The black line, or the red line, represents the concentration by volume that's plotted on this axis. So we have a watershed here that would generate, say, a typical 25-year or 50-year event, or 10-year event, mudflow event. So here's the hydrograph for this event. And then if we add the concentration by volume, I typically started at 20%, ended at 20%, because there is no such thing as a clear water flood event. And then increase it quickly on the rising limb of the hydrograph. As you approach the peak discharge of the water event, becomes highly diluted with water, and so the concentration begins to fall off. But the mudflow hydrograph with the bulk flow then looks like this black line. As you route this down the fan, then, if you routed the water event down towards the terminus of the fan, you would see this water event occur somewhere near the terminus of the fan like this. As the mudflow event was routed downstream, it continuously races to catch up, the peak flow to catch up with the frontal wave, and the frontal wave becomes even steeper, and you have a much elevated peak flow that would lag the water flow by some time period. Excuse me. The tickle. So in order to perform a mud flow analysis in Flow2D, you have to do several things. One is, in the control.data file, you switch on the mud flow. Now, if you're in the GUI or in QGIS or something, you'll do this graphically. But I do this for you because this is the way that I typically do it. I just go to the con.data file in WordPad and hit the fourth parameter in the second line and change it from 0 to 1. Turn off your conventional sediment transport if you had it on. And any generic bulking factor that you might have, if you were just doing clear water flow, say at 10 or 20%, and you just wanted to bulk the entire thing to see what effects having sediment, a low sediment concentration in your flow event would have in your water event. Then you need to add one line in sediment sed.data. And this is just the coefficients and exponents that I showed you for the viscosity and the yield stress in table 9. That's a typo. So this would be a line, one line in sed.data, and it would be M for Mudflow, coefficient and exponent for viscosity, coefficient and exponent for yield stress. The 2.74 represents the specific gravity, might be slightly different than 2.65. You could probably use 2.65. I just have this for the mixture of the specific weight mixture in the model. And then this is the K factor, 0.0 is the K factor, the laminar flow end value. So this is all you need. Everything else is internal to the model. All the computation of the yield stress and viscosity, all of the balancing of in the momentum equation and in the yield stress equation for viscous versus dominant viscous stresses versus dominant turbulent dispersive stresses. All of this is then enabled in the Flow2D model by this one line code. Now, the other thing you need is with your inflow hydrograph, where you have time and water discharge, is a concentration by volume in the third column. So in your inflow.data, the file that normally consists of just time and discharge, you now have to add a third line of concentration by volume. Now, when you do this, you will generate in the summary.out after a simulation is complete. You will be able to look at the inflow hydrograph, and based on your sediment concentration volumes that you've input into this sed.data file or inflow.data file, and you'll see here again, just to highlight what I discussed before, my cursor, 20% concentration on the initial limb, a high concentration with the arrival of the peak of the frontal wave, and then as you approach the peak discharge, it dilutes some and it's diluted more on the falling limb. So when you run this and you bulk this hydrograph for all this spatial or temporally variable inflow hydrograph, and if you have more than one inflow hydrograph, you have coalescing alluvial fans or something, you can put them in with their own individual concentration by volumes. And what the model will do internally is it will track the water and the sediment volume in each grid element separately and calculate as temporally and spatially varied the sediment concentration by volume. So when you're done and you look at the summary.out file, you'll see the water and the bulk volume of your inflow hydrograph. That's this right here. This is the sediment volume. It will compute this for you and report it here. So what this means is that the sediment volume is the bulked volume minus the water volume. So it's 36 minus 22, it's 14 acre-feet of water. And this would result in an average concentration by volume on the order of 38%. So for you to have a mud flow that then has a concentration that's going to flow as a mud flow on the rising limb of the hydrograph, or maybe throughout the whole thing, in which case, like in the Swiss ones, this would be more uniformly 40% or 50% concentration by volume. Whoops, sorry. You would need to have, because you have these 20% concentration by volumes on the rising and falling limb, you would have to have a concentration, average concentration for your entire event of somewhere on the order of 25 to 35 or slightly higher concentration by volume in order to generate a mud flow event in your hydrograph. Got that? So you need to have something on the order of around 30% or slightly higher in order to have in order to generate a mud flow volume in your simulation. Now, I X these out because I recently did this, because what this does when you run a mud flow event, it's routing this flow and it's ceasing the flow or remobilizing the flow in individual grid elements depending on whether the flow stops or not. It's routing the entire bulk flood event. It's routing the bulk sediment. It's not routing the water, it's routing the sediment. But I was always back calculating the water volume. And it was brought up to me that this lends some bit of confusion to this, because it's not routing water at all. This is only a calculation that's made at the end of the simulation to identify how much water was in the street storage, or how much water. And this doesn't mean anything, because it's actually just sitting there as a bulk sediment volume. So I have since eliminated this column and just reporting on what the actual routing is. That makes it a little more clear for you. Now, another way to perform this, and we'll talk about this more next week, is to add the sediment volume directly to the inflow.data file. So you would need to go out in the field, look at the conditions, look at how the sediment's arriving to the water course. It may be through landslides, through erosion of the channel bed and banks, scour to bedrock, overland sediment yield and sheet flow, whatever the sediment loading physical process is. If you could identify that and estimate it, then you could add the volume directly into the inflow.data simply by putting in a number greater than 1. The model would recognize if it's less than 1, it's a concentration by volume, or if it's greater than 1, it's the actual volume in either cubic meters or cubic feet of sediment. And that's solid volume, not volume that's sitting on the ground as a porosity, but it's as a solid volume of sediment. So when you do these mud and debris flow flood hazard simulations, I would recommend that you provide to the client water flooding, low sediment concentration, maybe with bulk flows, and you could have a uniform X concentration variable assigned at 20% in cont.data, and this would uniformly bulk everything. You wouldn't have to add anything to your inflow.data file to do this low sediment concentration with bulk flows. Then you could do mud flows where the concentration gets variable and higher than 45%. And I would do your bulk flow for maybe the 10 and 25-year events for mud flows, and then just bulk flows for lower concentrations for the 100-year event, because it is unlikely that your watershed is going to be able to generate a mud flow for the 50-year event and higher, because there's just too much water in the 50 to 100-year flood event. So if you do the hydrology for the 50-year flood event, and then you estimate the sediment load that you think you could get out of the watershed to the fan apex at the canyon mouth for the 100-year event, and then you calculate the average concentration by volume from that, you're going to see that it's probably going to be less than 20% concentration by volume. In other words, it doesn't mean that you might not have some surging, some frontal waves with debris, but you're not going to have a viscous mud-like, cement-like mud flow that we saw going through that log mill for a hydrologic event, which is on the order of a 50-year or 100-year event. Typically, in order to have a 100-year event that might generate a mud flow, it's going to be completely a landslide event that's going to come through onto your fan. And so I suggest that you remember that and recognize that your mud flows typically will occur for a 10 or 25-year hydrologic event, and that if it's a higher or less frequent event, higher magnitude, less with more water volume, that it's going to be more diluted and more on the order of a mud flood or just a low sediment concentration flooding event. And then in an urban area, you need to consider the effects of all of the development, the hydraulic structures and other flood control features, etc. So we're going to talk about sediment delivery and generating a mud flow, and how to rationalize what I just talked about next week. So to wrap up this week's effort, I'm going to show you a simple example here from Bernard Creek in Centerville, Utah, a model that I made. And in this case, this alluvial fan was subjected to historic mud flow events. And they built a little debris basin here, probably just off the cuff back in the 80s, 90s. And they didn't have any practical means of estimating this, because the mud flow event for the 50-year event is like 6 orders of magnitude of what could be stored in this little basin. So anyway, there's a little bit of deposit in this basin, and it overtops and goes right down this very steep average 10% slope to down the street through these houses and stuff, and then flows directly into the school. And what's kind of unique about this is, I think if you look at this, there's a dip in this street here, or a steepness in the street. And this is probably the range at which the mud flows occurred and then deposited over geologic time and generating this alluvial fan surface. And then the less viscous mud floods that occurred in between periods of recharge for the mud flow events flowed further and carried material past. So there might be a delineation here geomorphically of the mud flow extent of this fan in geologic time. So here's looking down this street, the steepness of the street, houses on both sides, again the school downstream. So this is a very simple model. It was actually developed back in the early 90s, and I still use it to demonstrate the impacts of mud versus water versus having streets and versus rainfall and mud. So I'm going to run these, hopefully. I tested these before we started. And so this is a very steep slope, small debris basin, stores some of the event at the beginning, and has numerous buildings which are modeled and so forth. I'm actually using an older model on this too. So right now it's raining in the upper basin, and some of the materials coming down, and it's storing in the basin right above the alluvial fan. Now here comes the mud flow down the streets, gets in and amongst the buildings, gets to this cross street, and then piles up around the school building right here. Okay, so that was the mud flow that occurred. We conserved volume exactly here. And when it's done, you will see that the mud flow didn't enter the school obstruction buildings, but that there was pretty high flow depths in front of the building and in the main street, but as it got off into the neighborhood, it wasn't so high. Now, what I'm going to run next is so that you clearly see the difference of this and water, what mud flow versus a watery flood event would do. And this has no sediment in it at all, nor is it bulk. So you'll see shallow overland flow. Again, it's storing in the basin. Here comes the flood event. Most of the flooding is confined to the streets as conveyance features. Get a little higher depth here again in front of the school building, but it's shallow flow, watery flood event everywhere. So you get the idea. Now I'll show it without the streets. Now, obviously, your model is going to have smaller grid elements. It's going to have a lot more urban detail, perhaps, be a much larger model on the order of maybe 1 million elements or so. I'm just showing this because it's very simple to understand and so forth. And I'll show you some results next week of some actual mud flow models. But here what you see is that the mud flow frontal wave actually occurred, and the peak of discharge of I took the streets out, ran the mud flow model again, and you saw the peak come down, get onto the alluvial fan, and without the streets conveying the flow down to the terminus of the fan, the mud flow essentially stopped. It didn't even make it to the end of the model simulation. And this is somewhere in the area of that, decrease in the steepness of the slope, that it ran out of steam and essentially stopped moving. Okay. So now I'll show you the timing of the flood event, which may be important. So if the rainfall is going to occur on the alluvial fan, roughly about at the same time it occurs in the upper basin, you'll see it start to rain here on the alluvial fan also. So here it is, raining, and now it's coming down, fills the basin, and now you see more of a dilution of the flow on the fan by the rainfall. Here the rainfall is being driven. It's 2.5 inches in roughly 2 hours or so, and it's complete at that point. And so you see the depths are not as deep. We don't see any red down in front of the school front here at all. So my point of this is that adding the rainfall to this alluvial fan simulation has two values. One is that it accurately ties the timing of the rainfall and the mud flow on the fluid for the overall event, and it dilutes the mud flow as it moves. So you have to delineate whether or not you're going to have mud flow from rainfall only in the upper basin or as a landslide, or the storm is big enough, it may be more or less centered over the watershed, but it's also occurring on the alluvial fan. And in different parts of the western United States, these alluvial fans may be on the west side or the east side of the valley. So there may be a timing issue of the storm as it moves across the valley. The storm might occur on the alluvial fan first if it's on the east side of the valley, and then move up into the upper watershed. Or if the watershed and alluvial fan is located on the west side of the valley, the storm may occur in the upper watershed first and then move down onto the alluvial fan. Those are some considerations. Okay. So I did that for the edification, for your edification, to show you some differences. One thing that you could do, I'm just mentioning this, is that you could put in building collapse vulnerability curves into the model and actually have the mud flow wipe out your buildings based on the fact of whether they're good buildings, moderate buildings, or poorly constructed buildings in terms of velocity and depth. Would wipe out the building and allow the flow to go through the building and down fan. And this was somewhat important to modelers in Italy and Switzerland and Europe. So I put this in for them just so that you know that it's there. Now, next week I'm going to talk about mudflow sediment supply. Obviously, the mudflow component in Flow2D is important because people use it for modeling the tailings dam breaches. And one of the things that we are starting on now is a two-phased flow model so that you can run the Flow2D model with a storage of water over top of sediment, stored tailings dam sediment, and have it flow both as highly concentrated conventional sediment load as the water drains from the tailings dam reservoir if there's water sitting on top, or as or as a mud flow underneath the water until the water's drained away from the sediment. And I've started programming that, and I have it completely conceptually outlined how to do it. We would track the sediment volumes in both models and have vertical exchange in both directions for the mud flow to the conventional sediment transport, and from the conventional sediment transport depositing back to the mud flow to keep it moving. So that will represent a better opportunity to model those kind of tailings dams conditions that have the water sitting on top or having an inflow hydrograph to a sediment, to a tailings dam. Now we have some tailings dam webinars that we've done in the past, and I think Noemi's presented a couple of them. You can download them at the Flow2D website, and she would show you what we're doing right now in order to mix the water and the sediment as a continuum to route downstream as a tailings dam breach. And there's a lot of tailings dam scenarios that are being, or projects that are undergoing or underway worldwide right now with Flow2D. So with that, let me see. I'm going to do two things here. I'll stop the recording, hopefully. Let me see. I can do this. Options. This has changed slightly on me. I don't see where I stopped the recording. Bear with me a second here and I'll do this, and because then I can see, well, let's just go ahead and open questions and see what questions there are, and I'll just record this too. So here's, I think this is all the questions. Says, so Jim, the sediment concentration by volume represents the CV concentration range of values. It's by Roberto. Let me see if I can expand this so I can get the full question. No, not the way to do that. I've closed the questions. I'm sorry. I have to apologize for this. These GoToWebinars, they keep changing the format on me and so forth, and maybe I closed the here's the questions. Let me double click on this. Okay, so maybe I can open this one. Boy, am I incompetent. Karen, help me. I don't know. Maybe I can pull this. Karen, are you there? I don't remember how to expand the questions and answers. Oh, here. Okay, so I'm back to the panel. Hi, is this, well, I didn't answer this fully, but because I can't see the whole question. I'm not sure how to expand the question line. Oh, here, maybe this will help me. If I can hold it. Yeah. Oh, come on. Okay. So the sediment concentration by volume represents the CV range of values. Is that correct? Well, it represents the entire flow value. So you could model this. You could model clear water river inflow, and then have the mud flow enter the stream, flow down to a reservoir, and it would represent the full range of concentration by values from 0 all the way to 50% concentration by volume because it's spatially delimited. It says, yes, we always make our recording available to attendees. Is the hyperconcentrated flow, is it assigned to the mud flow values reported? It needs to be assigned to the mud flow values reported in the table. Well, yeah, I mean, it represents the mud flow values reported in the table. Yes, that's right. You're going to, what will happen is from 0 to 20%, the model will just route the sediment as a bulked volume. Above 20% concentration by volume, the effects of the viscous behavior for the yield stress, laminar resistance, and the increasing concentration for the dispersive stress become relevant. They won't really become relevant until 25 or 20 or 30%, but I allow the component, the mud flow component, to start computing what the effects are on the flow at 20%. So the discharge can be adjusted using a rise of 20% as a rule of thumb for mud flows. Yes, that's true. I like to start it at 20% because then the mud flow component is always invoked or engaged. Could you also provide more information on what type of fluids, tailings, flow from an extreme rainfall, generated what type of flow being recorded in the videos? You know, I think most of those, the Swiss video where the people were shown jumping out of the way, I think that was sort of a landslide event. But as you saw, the storm was over the whole valley. So even though it might have been a landslide, it might have been stimulated by a hydrologic event where the slope instability became a prominent factor and a landslide occurred. I think the other events were more of a hydrologic, or at least the mud flood event was a hydrologic event. The other mud flow event might have also been somewhat of a viscous type of mud flow associated with a landslide, a big landslide. Could you also provide more okay, sorry, I did that one. Flow 2D has the possibility of landslide and laminar events. Yes and no. People have done it. I think if you're into the lower end of the landslide, that is, it really is flowing as at least a plastic fluid, you could do it. But if it's a tumbling type of block failure event, which is sliding and tumbling, then no, I would not do that. Some consultants have used it in California to model some mud flows that occurred and replicated the event fairly accurately using Flow2D, but I would not generically assign that to be the case. When we add volume in the hydrology, when we add volume in the hydrograph, what coefficients I think they're suggesting do we use? Again, you need to go to the table and have a physical sense of what you think the mud flow will behave like. Is it wet cement, or is it kind of like a muddy flow of water, or is there very little clay in it, and so forth? And then base the selection of the parameters on that type of event. And that's regardless of whether you do the concentration by volume or the actual volume in the mud flow. I would love to see videos of mud flows, please. Email me if you want to download those. I think even Karen might have those on the website, but ask her about those if you want to see some of those. I have others too, but if you want to see the mud flows that I showed here, either email me directly or just email contact@Flow2D, and Karen might be able to direct you to those. Looks like I have some more. How can we watch this seminar again later? Well, again, Karen will post this to the website. She has all of the videos, and I think she has you on the mailing list if you're watching this. So when she posts this, she will alert you to the fact that it is posted and where to download it. And it takes her 3 or 4 days for me to convert the recording and then have her post it. So look for this within a week or so. In a case where I have granular metric data and Atterberg limits, is it okay to choose a sample volume just having the data for the yield stress and viscosities? If the soil samples from the best investigation have all the data? Yes, that is very intuitive and appropriate. I have in the papers that I wrote and in my PhD dissertation, the both the sediment the clay concentration, some plastic index values, and all the data that you would have normally with that. You could, if you have that data associated with another event and you pay for getting the hydrometer analysis and doing the plastic and the Atterberg limits and so forth, yes, you could compare that with other published data and make a reasonable, educated selection of the sediment concentration by volume. The rheologic model uses a specific mud flow which behaves according to the Herschel-Buck or the MAU or other comparable model. I would say that it's similar to the Herschel-Buckley, but it's not set up exactly the same way because I have the yield and viscous stresses as well as the turbulent dispersive stresses in the same model, and they balance each other. So if you have something that's in the middle of being a mud flow versus a mud flood, it will actually balance that yield stress and then put it in the momentum equation and route it. So the idea is that you can model the full range of viscous behavior to turbulent dispersive behavior in the Flow2D model. And I don't know if you can do that in these other rheologic models. So I think that's it. And if you have any personal questions regarding this, you can again email me at jim@flow2d.com. So I'm going to stop the the webinar now, and thank you for attending, and join us again next week. And I'll try to have some more more complex urban simulation of Mudflow, as well as talk about Mudflow, generating Mudflow yields from watersheds to complete this analysis. Okay, so thanks and bye.